In this video, I'm going to talk about applications that involve using cross products. Cross products are used extensively in physics and engineering applications, and there are two applications of cross products that come up quite frequently. Torque is a measure of the force that is required to cause an object to rotate or to change the rotation of an object. A wrench that is used to loosen or tighten a bolt is one example. Magnetic force on a moving charge is another example. A particle with a given charge will change its path in response to the force exerted by a magnetic field, and this change in path is described by the cross product. Now let's look at an application that involves torque. Torque is the result of a force that is applied to a pivot point through some distance. Torque is a vector quantity. So the symbol used is a vector symbol with the Greek letter tau representing torque. Torque is the cross product of the vector r and the vector f, where the vector r is the vector that represents the displacement vector from the pivot to the end of the torque arm, and the vector f is the force that is applied. The magnitude of the torque is given by the magnitude of the vector tau is equal to the magnitude of the cross product of r and f, which is equal to the magnitude of the vector r times the magnitude of the vector f times the sine of theta, where theta is the angle between r and f. Note that there will be a maximum torque when f and r are orthogonal vectors, meaning theta is pi over 2. So let's work an example. A pump handle has a pivot at the origin with coordinates 0, 0, 0, and the pump handle extends to the point P, represented by the coordinates 5, 0, negative 5. A force F in component form given by 1, 0, negative 10 is applied at point P. I want to find the magnitude and direction of the torque about the pivot. We have the vector for F, and we need to identify the vector for R. Conveniently, because R is at the end of the pump handle and the pivot is at the origin, my R vector is given by 5, 0, negative 5. The torque is the cross product of the vector R and the vector F, so I set up the determinant of a 3 by 3 matrix, with the first row populated by I hat, j hat, k hat, the second row populated by 5, 0, negative 5, and the third row populated by 1, 0, negative 10, which is equal to the determinant of a 2 by 2 matrix of 0, negative 5, 0, negative 10 times I hat, minus the determinant of the 2 by 2 matrix 5, negative 5, 1, negative 10 times j hat, plus the determinant of the 2 by 2 matrix 5, 0, 1, 0 times k hat. This gives me the torque vector is represented by 0 I hat plus 45 j hat plus 0 k hat, or in component form 0, 45, 0. The magnitude of my torque is 45. The direction of the torque is in the positive y direction, which is easy to see when I look at the component form of my vector. Now let's talk about a magnetic force on a moving charge. Moving electric charges experience a force when they move through a magnetic field. An electric charge has units of coulombs, and magnetic fields have units of Tesla. Coulombs is represented by capital C, and Tesla is represented by capital T. 1 Tesla is equal to 1 kilogram per coulomb second. For an isolated charge that's denoted by little q, moving with a velocity v in a magnetic field which is denoted by a vector quantity capital B, the force F that the charge experiences is given by the force is equal to the charge q times the cross product of v and b. The magnitude of the force is given by the magnitude of q times the magnitude of the vector v times the magnitude of the vector b times the sine of theta, where theta is the angle between v and the magnetic field b. So let's work an example. A proton, which has a charge of 1.6 times 10 to the negative 19th coulombs with a velocity of 2 times 10 to the 6th meters per second in the j hat direction, experiences a force in newtons that is given by 5 times 10 to the negative 12th in the k-hat direction as it passes through the origin. I want to find the magnitude and direction of the magnetic field at that instant. The force in component form is written as 0, 0, 5 times 10 to the negative 12. And the velocity in component form is written as 0, 2 times 10 to the 6th, and 0. Notice that F is all in the k-hat direction, and V is all in the j-hat direction. This means that in order for F to be orthogonal to both V and B, the magnetic field B has to be a vector in the component form B, 0, 0. The charge Q is 1.6 times 10 to the negative 19th. The force is Q times the cross product of V and B. This means that 5 times 10 to the negative 12th in the k-hat direction is equal to 1.6 times 10 to the negative 19th times 2 times 10 to the 6th in the j-hat direction crossed with B in the i-hat direction. I'll divide through by the charge, and I get 5 times 10 to the negative 12th over 1.6 times 10 to the minus 19th in the k-hat direction is equal to the determinant of a 3 by 3 matrix populated with i-hat, j-hat, k-hat, 0, 2 times 10 to the 6th, 0, B, 0, 0. This determinant is negative 2 times 10 to the 6th times B in the k-hat direction. If I divide through by negative 2 times 10 to the 6th k-hat, I get B is equal to minus 15.625. This is the only non-zero component in the vector that represents my magnetic field. The magnitude of my magnetic field is 15.625, and the vector for the magnetic field is given in component form as negative 15.62500. This tells me that my magnetic field is in the negative x direction. Now you get to try it. Pause the video and find the magnitude and direction of the force that is acting on a particle when the particle has a unit negative charge of Q is equal to negative 1 and it enters a constant magnetic field given by the vector B is equal to 5k hat with a velocity of the vector V is equal to I hat plus 2j hat. When you're ready, restart the video to check your understanding. In order to find the magnitude and direction of the force on this particle that has a negative charge of Q is equal to negative 1 in a constant magnetic field given by 5k hat with a velocity of I hat plus 2j hat, I need to find the force equal to the charge times the cross product of V and B. My force is equal to negative 1 times the vector I hat plus 2j hat cross 5k hat. I set up the determinant of my 3 by 3 matrix, keeping in mind that I'm multiplying by negative 1. So I'm looking for the negative of the determinant of I hat, j hat, k hat 120005. This is equal to minus the determinant of a 2 by 2 matrix 2005 times I hat plus the determinant of the 2 by 2 matrix 1005 j hat minus the determinant of the 2 by 2 matrix 1200 k hat. In vector component form, my vector is negative 10 I hat plus 5 j hat minus 0 k hat, and in component form, I get negative 10, 5, 0. The magnitude of my force is given by the square root of 100 plus 25, which reduces to 5 square root of 5. Theta is the inverse tangent of negative 1/2, which is approximately 153.435 degrees, or 2.6779 radians. This is the magnitude and direction of my force. These are some great examples of common applications that will involve using cross products. Be sure and let me know if you have any questions.